Welcome to Recitation Chapter 5. Chapter 5 talks about gases, and we'll be doing stoichiometry of gases. We'll talk about some gas laws, partial pressures, and how to do calculations. The important thing for this chapter is the equation PV equals nRT. Perv nert. Now, you can get everything from this equation. So if you need Boyle's law, and you do need to know the Boyle's law says that pressure is inversely related to volume. So it's about pressure and volume, PV here. So if you make everything a constant, just call it K for constant, and you solve PV equals K in terms of P, you have a constant divided by V, and you can see that pressure is inversely related to volume. So as one increases, the other decreases. This is what I love about the perv nert equation, because you only have to memorize the perv nert. So PV equals nRT for Charles' law. Well, what does Charles' law relate? Volume to temperature. So if everything else is constant, then if you solve in terms of V, it's where's the V and the T. So here we have volume is directly proportional to temperature. So as temperature decreases, the volume will decrease, which I think you saw that in the recitation or the video, the lecture video with the balloon and the liquid nitrogen. The other thing is sometimes you will have to do different states, like P1 V1 equals P2 V2. So you have an initial pressure, initial volume. You might have to solve for a later pressure, and this would be the equation. So how would you get that from PV equals nRT? Well, here's the P and the V together. So you can just do PV1 equals PV2. Same thing with the temperature. Okay, so you start with how is, so when you want volume, if you want the temperature to come over here, so V1 T1 equals V2 T2. And that's in another equation. So what I'm trying to show you is that you really don't have to memorize anything but PV equals nRT, and you can derive, with that you could probably only have to memorize two equations, PV equals nRT and the density equations that we'll talk about. The other thing that confuses students sometimes is what units does everything need to be in, because these equations with the gas laws do require certain units for pressure, and I don't like to memorize that. So what I do, and you should have this on your periodic table that you'll have for your exam, but R is 0.08206, and as many times as you work these problems, you'll know that, and it's liter times atmosphere divided by mole over Kelvin. Those are the units you want everything in, because that's what it needs to cancel out. So you want your volume in liters, so V in liters. You want your pressure in atmosphere. You want your stoichiometry amounts, not grams and kilograms. You want that in moles, and you want your temperature in K for Kelvin. So a lot of times you'll get something like 0 degrees Celsius, and you're going to have to convert that to Kelvin. So we add 273, and then that would be 273 Kelvin. So you add 273 to any of your degrees Celsius, and that'll give you your Kelvin. And you do have a few ways to convert, like 1 atmosphere equals 760 millimeters of mercury. So if you're given your pressure in millimeters of mercury, you can convert that to atmospheres. So you do need to memorize that conversion factor. because to work these problems, these are the units you're going to have to work with. Alright, so we're going to get going, but I wanted to tell you what problems that are required. The problems that are due for this chapter for recitation are problems 5.1, 5.3, 5.5, and 5.6. This is problem 5.1. A mixture of argon and neon has a measured gas density of 1.35 grams per liter at STP. Assuming ideal gas behavior, what is the average molar mass of the mixture? What is the percent composition of argon and neon in the mixture? The first thing you need to do is define what STP is. STP, and this is section 5.5 in your TRO book, page 209. And it talks about molar volume. So when you have molar something, that's usually 1 mole equals something. Because like molar, so molar volume, 1 mole of gas equals 22.4 liters. And that's at STP. And that's the volume that any ideal gas is going to have if they're 1 mole. It's kind of interesting, actually. How big is 22.4 liters? It's the size of a basketball. So I visualize this basketball full of gas if it's 1 mole. And but it's only at STP. So that means your temperature is 0 degrees Celsius, which is what? That's right, 273 Kelvin, because you're going to have your temperature in Kelvin to work these problems. And pressure is 1 atmosphere. And that's typically what atmospheric pressure we're at, 1.00 atmosphere. So now, when you see STP, just go ahead and define that and know that you do have this conversion factor. That conversion factor only works at STP. Sometimes you don't need that conversion factor. Sometimes you won't use it, and sometimes you will. So here, when it's talking about density, there is one other equation that you need to know besides PV equals nRT. And this is density equals PM divided by RT. And your book goes into how to derive that through PV equals nRT. And that is fine. For time's sake, I'm not going to do that here. But you will need to, when you're dealing with densities and you're talking about average molar mass, that is this cursive looking M, and the density is D. So when I see these words, density and average molar mass, I know that this is the formula that I need to use. So I do have that memorized. Okay, so now we look, this is typically how we solve all these problems, we look for the other variables. So we're going to solve in terms of what the question asks. What is the average molar mass? So we need to solve in terms of M. So this is going to be density divided by RT. Actually, that's not right, is it? It's going to be density times RT divided by P equals M. So if you isolate your variable, and then I like to isolate my variable for what the question's asking, and then I like to define all my variables. So we have R, that's your gas constant, right? 0.08206 liters times atmospheres all over mole Kelvin. I always write that out first, so then I make sure that all my variables are in terms of those units for this equation. And then I also make sure that when I am solving, I keep my units and I rewrite them to make sure they cancel out, because that's a check for me to know, oh, I'm pretty confident I got the right answer. Density here, the density is given to you, and it's 1.35 grams per liter. And this is going to be fine here with grams because what's molar mass going to be? What's the units for molar mass? Grams per mole. Those are your units. So that's what your units are looking for. So there's where the G is going to come from. Temperature. Temperature, well, they said STP. So your temperature is going to be 273 Kelvin. And your pressure is going to be 1 atmosphere. 1.00 atmosphere. So now it's just a matter of what I call plug and chug. And we will solve for molar mass. 1.35 grams per liter times 0.08206 liter atmosphere mole Kelvin times 273 Kelvin all over 1.00 atmosphere. And then I like to make sure my units cancel out. So liters, liter, atmosphere, atmosphere, Kelvin, Kelvin. And we're left with grams per mole, which is the units for molar mass. And that works out to be 30.2 grams per mole. If you multiply and then divide. And that is the average molar mass of the mixture. Then the question is, what is the percent composition of argon and neon in the mixture? This is a little tricky. Do you remember last chapter where we talked about the average molar mass and our formula? Do you remember what our formula was? So we took whatever the mass was and we took it times the percent abundance, and then we added another mass times the percent abundance. That's how you do the average. It's like a weighted average, and you sum all that up and it gives you one number. This is actually how we calculate your grades in this class. Well, Canvas does. Okay, so they give you, in this problem, they give you argon and they give you neon. So, and you have the average here. So the answer is 30.2 grams per mole. And there's only 2 here. So we're only going to need 2 terms. And that's kind of nice because if you have 100%, if something's 40%, what's the other? 60%. Something's 30%, because they got to total up to 100%, the other 70%. So what you can do here is you can look at the periodic table and look at the molar mass for argon. These are noble gases, so they're in the last group. So argon would be 39.948 is its mass, and we don't know. We got to solve for x. We don't know its percent in this. That's what we're trying to figure out. And then we're going to have the other one. So this is argon. What's the other one? Neon. So we see that neon is 20.1797 grams per mole. We can do grams per mole here. And we want this in terms of x. So like I said, these, since there's just 2, this one's going to be 1 minus x. That's going to be your equation. So if you find the percentage of whatever x is for argon, then you subtract it from 1 and you'll have the percentage of neon. So now you have to do your algebra 1 where you solve for x. And when you do this, it should work out to be, basically I can go through the long term. 39.948x plus 20.1797, because that's multiplied by 1, and then you minus, because you're multiplying by x, 20.1797x. This is from this term here, minus x. and then this equals 30.2 grams per mole. Now, we have a term without an x and a term without an x, so we are going to get those terms on the same side of the equation. So 39.948x minus 20.1797x equals, we're going to bring this term over, and since it's a positive here, we're going to subtract it, right, from both sides of the equation. So it's going to be 30.2 minus 20.1797. And then you will have, you can subtract these two, and so you end up getting 19.76x equals 10.02 grams per mole. And then you divide both sides by 19.76, 19.76, and the answer is 0.51 for x. So in terms of percentage, you times this by 100, and that's 51%. What was x? Argon. So what's 1 minus 0.51? That would be 0.49, right? So 49% is going to be your neon. This is problem 5.2. Put this up here. And in this problem, it says if 7.50 liters of water vapor at 50.2 degrees Celsius and 0.121 atmosphere reacts with excess iron, how many grams of iron 3 oxide will be produced? Now, I love it when I see excess iron because that tells me, oh, I don't have to do a limiting reagent and figure out how many grams of or moles of the product are going to be formed. So it saves me a good 5 minutes. Okay. Now, what variables are we given? We're given 7.50 liters. We're given temperature, 50.2 degrees Celsius. We're given atmosphere. And it's asking how many grams of iron oxide, which is here, iron 3 oxide, will be produced. So the question is, how many grams is this going to be produced? So this is stoichiometry. And when you solve these gas equations in terms of liters and degrees Celsius and atmosphere, we need PV equals nRT. Now, we talked about last equation. When we're dealing with stoichiometry, we need things in terms of moles. Okay, so in this equation, your moles are N. N is the moles of gas. So we need to solve this equation in terms of moles. Because if we get moles of, they said water vapor. So we're going to change substances here. We can solve this for moles of water by solving this equation for N. And then once we have moles of water, we learned from last chapter, we can use the coefficients in front of the chemical compounds to go from mole of one substance, here we'll go from mole of water, to the mole of iron oxide. And what are those coefficients in front? This is our conversion factor we're going to end up using. So we're going to have 3 moles of water equals 1 mole of iron oxide. So the key here is to get mole of water to be able to do the stoichiometry for how much iron oxide will be produced. So we solve this PV equals nRT in terms of the N. So this equation works out to be PV divided by RT. And then we're going to, now that we've isolated our variable that we want, which is N, number of moles of water, that's what they're giving us information on, we're going to fill in our variables. So what did I say? I always like R first. It's our constant. It's always 0.08206. And I like to write liters atmosphere over mole Kelvin, because then I do a check to make sure all my variables are in those units. Otherwise, I'm going to have to do some math. Now, What's our pressure? Yes, there's the pressure. 0.121 atmosphere. That's exactly what we need, atmosphere. What is our volume? 7.50 liters. It's in liters. We got liters in atmosphere. We're good there. Temperature. What's our temperature? 50.2 degrees Celsius. Can we put that in the equation? No. We need to turn that into Kelvin. So we're going to add 273 onto the 50.2, and our temperature will be 323.2 Kelvin. And you don't have to take it out to 0.15. You don't have to do that. You won't have to do that for an exam, okay? So just remember 273. All right, now we've defined our variables, and we are going to solve now for N. We're going to plug and chug. So let's do this. N equals pressure 0.121 atmosphere times the volume 7.50 liters, all divided by your constant R, 0.08206 liters atmosphere mole Kelvin, times our temperature in Kelvin, 323.2 Kelvin. Now, what I like to do is I like to check off my units to make sure that N is going to be in moles. Atmosphere, atmosphere, liter, liter, Kelvin, Kelvin. And so there's the mole. So when you put this in your calculator, 0.121 times 7.50, all that divided by 0.0206 multiplied by, I would multiply these terms on the bottom, and I would multiply these terms on the top, and then divide them. And your answer for that should be, number of moles is the moles of water then would be 0.0342 moles of water. Now, what it asked for was how many grams of iron oxide. So let's do our conversion, our dimensional analysis, where we put 0.0342 mole of water over 1, and then we're going to go from mole of water to mole of iron oxide. And it wants grams of iron oxide. So we're going to use the molar mass, 1 mole of iron oxide, and then if we look at the periodic table and we add 2 irons plus 3 oxygens, you should get 159.69 grams of iron oxide. And then what's the numbers that we put here for mole of water? Yes, the coefficients. So for 3 moles of water, we have 1 mole of iron. When you put that in your calculator, 0.0342 divided by 3 times 159.69, you get 1.82 grams of iron to oxide. And that is your answer. This is problem 5-3. And it gives you a chemical equation. Ammonia, NH3, may react with oxygen and form nitrogen gas and water. Okay? And there's your equation. Now's the numbers. You got 3.65 grams of ammonia. You reacts with 5.48 grams of oxygen. So obviously you know this is going to be a limiting reagent because you're given both amounts, gram amounts of both reactants. And it tells you what it produces. It produces, so when you do PV equals nRT here, you got to look at the substance, the liters of nitrogen. So if you did PV equals nRT, you're dealing with moles of nitrogen. because you're given the volume, you're given the temperature, and the pressure. So the first thing to do is to figure out, like we always do with limiting reagent problems. We'll make this number 1 here. We'll come down here and we'll solve for number 1. What do? You convert the amounts of your reactants into your moles of product. So we have 3.65 grams of ammonia over 1. We look at the periodic table and we calculate the molar mass of ammonia, which is 17.03 grams of ammonia for 1 mole of ammonia. And then we're going to do our mole-to-mole bridge where we can go from a mole of ammonia to moles of nitrogen. That's our product. And what's our coefficients? This is a 4. So 4 goes with ammonia. And this is a 2. And the 2 is going to go with the nitrogen. And that works out to be 0.107 mole of nitrogen. And now we have to do the same thing for our oxygen. We are given 5.48 grams of oxygen. And we look at the periodic table, 16 times 2, 32.00 grams of oxygen for 1 mole of oxygen. And then we're going to go from mole of oxygen to mole of nitrogen. And where are we going to get those numbers? Our oxygen has 3 and our nitrogen has 2. And we put those in our calculator and we get 0.114 mole of nitrogen. Okay, so the limiting reagent. What reactant is limiting? Remember, it is the one that's the least. So what's smaller? 0.107 or 0.114? That's right. So your limiting reagent, what reagent is limiting would be the, not nitrogen, that's your product, ammonia, see? So it would be NH3 is your limiting. What is the percent yield of the reaction? Now this is where you need this here. What is the equation for percent yield? You have to have that memorized, right? So percent yield equals actual over theoretical times 100%. Now we're going to term, as long as our units are the same for actual over theoretical, like if you solve things in terms of grams, then you need grams of actual over grams of theoretical. You can also solve things in terms of moles, but you got to make sure that when you solve for your actual, that's in moles and theoretical's in moles. So in this case, we already have our actual. Okay. Do we have actual? I'm sorry, this is theoretical. This is theoretical. Yes, that's the thing here. So when we solve this, theoretically, this is the most that you can get because you only have 3.65 grams of ammonia. This is your limiting reagent. So your theoretical, you've already solved for. Theoretical is your limiting reagent, 0.107 mole of nitrogen. Now we need to solve for our actual. And the way we're going to do that is we're going to use the PV equals nRT. PV equals nRT equation. And then we're going to solve for moles. So we got to isolate our variable. So N equals PV divided by RT. And we're going to define our variables. So R is 0.08206 liters mole. I'm sorry. I was looking at something else. Liters times atmosphere mole over Kelvin. And our volume is 0.450 liters. And liters are good. Oh, we have our volume. Pressure is 1.00 atmospheres. You see that there. And our temperature is already in Kelvin, 295 Kelvin. So when we put this into our equation, N equals 1 atmosphere times our volume, 0.450 liters, divided by 0.08206, times our temperature, 295 Kelvin. When you solve that with your calculator, you should get 0.0186 mole of nitrogen. This is your actual. And I like to look at it and see, does that make sense? It is less than theoretical. It should be less than theoretical. When you're doing these, actual should always be less than theoretical. It's a smaller number, and it's in ratios part over whole. So let's put this into the equation for percent yield equals our actual 0.0186 mole of nitrogen over our theoretical 0.107 mole of nitrogen times 100%, and that gives us 17.4% yield. This is problem 5.4. Hydrazine, we're given a chemical reaction. A lot of times I check to make sure these things are balanced. They are balanced, so you're good there. But when I'm doing a problem anytime or whatever on the exam, I check, because if it's not balanced, you're going to get an incorrect stoichiometry answer. Hydrazine may react with oxygen to form nitrogen gas and water. So that's the equation that's happening. Now, if 3.95 grams of hydrazine into H4 reacts and produces 0.850 liters of nitrogen at 295 Kelvin and 1 atmosphere, what is the percent yield of the reaction? So the good thing is this is not a limiting reagent because you didn't get the amounts of oxygen, so you don't have to worry about that. We are basically, it does say what is the percent yield of the reaction, so I go ahead and write down the equation that you've memorized that you're going to have to use. Percent yield equals actual over theoretical times 100%. So we're going to have to define what's actual and what's theoretical. So once again, we're given the amounts, 3.95 grams of hydrazine, and this is to calculate our theoretical. So we're going to calculate our theoretical right here. So let's get moles. We're going to get this in terms of moles of nitrogen. So we're going to use molar mass into H4. The molar mass of hydrazine, then 2 nitrogens, 4 oxygens, is 32.05 grams per 1 mole of hydrazine. And then we're going to be able to turn that into moles of hydrazine for moles of nitrogen. What are our coefficients? There's no coefficients there, so that would be 1 and 1. You put that in your calculator, you get 0.123 mole of nitrogen. And that's our theoretical, because we start with 3.95 grams of hydrazine. That's the most that we can produce. Now we got to figure out an actual, and our actual is going to use PV equals nRT, and we're going to solve for N. So N equals PV divided by RT. And now we're going to define our variables. I like R first, so 0.08206 liters atmosphere mole Kelvin. Our pressure, what is that? 1.00 atmosphere. Our volume is 0.850 liters. And our temperature is 295 Kelvin. When we plug and chug, we get N equals 1.00 atmospheres times our volume, 0.850 liters, divided by R, 0.08206 liters atmosphere mole Kelvin, times our temperature, 295 K. And that equals 0.035 mole of nitrogen. Now that number should be less than our theoretical, and it is. So now that's a good sign, and we check to make sure our units cancel out, so we did everything correctly. And yes, we're given moles. So now to put it in, percent yield equals our actual 0.035 mole of nitrogen divided by 0.123 mole of nitrogen times 100%. Put that in your calculator, and I get 28.5% yield. This is problem 5-5, and it's just overwhelming at first when you're like, oh my gosh, I mean, that's a lot of words in that problem. And you know what, and most of these are, when you see a lot of words like this, just be prepared. It's usually the relationships like P1 V1 equals P2 V2, or it is the other law, which is Charles. I think Charles and TV. So I just remember PV equals nRT, and then TV. So V1 over T1 equals V2 over T2. So this is Charles' law. This is Boyle's law. And like I said, I just remember as that and solve things in terms of PV equals nRT. So usually when you get stuff like this, and then when you read it, you're looking for defining P1, V1, or V1 or T1, and solving for one of those variables. But let's read it just to make sure. Okay, a 17.0 liter helium tank is pressurized to 27 atmospheres. So they're giving you what? They're telling you a helium tank, and they're giving you volume is 17.0 liters, and they're giving you pressure 27.0 atmospheres. So this is looking a lot like Boyle's relationship. When connected to this tank, a balloon will inflate because the pressure inside the tank is greater than the atmospheric pressure pushing on the outside of the balloon. Assuming the balloon could expand indefinitely and never burst. So what is V2? Because the volume of the balloon will be expanding. Okay, those are volume terms. And never burst, the pressure would eventually equalize because the balloon to stop inflating. What would the volume, here it is, of the balloon be when this happens? Okay, so they're asking you for V2. Assuming that the atmospheric pressure, so they're telling you you're going from a 27 atmosphere pressure to P2 of 1.00 atmosphere. Assume ideal behavior. and constant temperature. Okay, so that's telling you you're going to have to use Boyle's law, and these are initials, so V1, P1. So then you use your equation. You've already defined your variables here. P1, V1 equals P2, V2. We want to solve in terms of V2. So we isolate our variable. V2 equals P1 over P2 times V1. I kind of do these like in little ratios here. And then I'm just going to plug and chug. I just make sure the units are the same, and it's always good to go with whatever the units are for R. You're safe. 27.0 atmosphere for P1 divided by 1.00 atmosphere for P2 times your volume 17.0 liters equals V2, and your atmospheres are going to cancel out. You'll be left with liters, which is a unit for V2. And when you do this, you should get 459 liters. Does that make sense? Well, let's think about the relationship. Your pressure is decreasing. So if pressure is decreasing, what happens to the volume? Okay, so the volume should increase. Because if you turns it into PV equals nRT, and you made this a constant K, then you solve for, in terms of P, it would be K over V, which means they're inversely proportional. So if pressure is decreasing, volume better increase. So then compare these. 17 versus 459, it is. Okay, good job. This is problem 5-6. And this is I think this might be one of your hardest problems. So let's work this problem. The picture below shows two bulbs connected by a stopcock. So they're separated. Okay, so you got nitrogen oxide and you got oxygen. And this is an initial volume, 6.00 liters of nitric oxide, and it has a pressure of 0.850 atmosphere. And the oxygen is in a 1.50 liter bulb and contains a pressure of 2.50 atmospheres. Now, then the stopcock is going to be open. And the gases are going to mix, and then you're going to get this chemical equation. Because when the nitric oxide reacts with the oxygen, a new gas is going to be formed, and it's going to be called nitrogen dioxide, which I think might be laughing gas. Okay? Now, this is a limiting reagent problem. See, determine which gases remain after the reaction goes to completion and calculate their partial pressures. If the gas was completely consumed, the partial pressure of that gas is 0. So when you find your limiting reagent, you already know that at the end of the reaction, its partial pressure will be 0. The temperature at the beginning and the end of the experiment is constant, 22 degrees Celsius. Now, there might be different ways to work this problem, but I am going to give you how I work the problem. Okay, so our plan of attack here. We need to figure out the limiting reagents. So we need to terms everything in moles. We go from, so our plan is to go from moles of each reactant of NO and oxygen to moles of product, which is the NO2 gas. But in order to get moles of nitric oxide and oxygen for each one, we got to solve PV equals nRT in terms of N. So when you solve this, you'll do N equals PV over RT. You're going to do this for nitric oxide, and you're going to do this for oxygen. And then when you do that, then you're going to do your stoichiometry where you do the moles to mole bridge to get the moles of NO2. And this is going to determine your limiting reagent. So let's just start there. So the first one we're going to do is NO. And we're going to use N equals PV over RT. And we're given the pressure of NO is 0.850 atmospheres times the volume, 6.00 liters, divided by R, 0.08206 atmospheres, liters per mole, or I'm sorry, what is that? It is liters times atmospheres over mole times Kelvin, and then it's at 295 Kelvin. How do we do that? We went ahead and just did 22 degrees Celsius plus 273 Kelvin, and that should be 295 Kelvin. We make sure our units cancel out: atmosphere, atmosphere, liters, liters, Kelvin, Kelvin, and that does give us moles. Moles of NO should be 0.211 mole of NO. Okay, so let's just keep on going with the PV equals nRT to get moles of oxygen. We'll put moles of oxygen here, O2. And so we're going to do N equals PV over RT. And for oxygen, we're looking at 2.50 atmospheres times 1.50 liters divided by 0.08206 liters times atmosphere over mole times Kelvin times 295 Kelvin. We put that in our calculator. We should get 0. Let's keep this in blue. 0.155 mole of oxygen. And let's make sure those units cancel out: atmosphere, atmosphere, liter, liter, Kelvin, Kelvin. Now, what we need to do is convert each one of these moles to our product. So we have 0.211 mole of NO over 1, and we're going to go from mole of NO to mole of NO2. And we look at our coefficients in front of our equation. And what coefficients of NO? Yes, 2. And what about NO2? 2. So this is going to work out to be 0.211 mole of NO2. And we are going to do the same exact thing for our oxygen. We got 0.155 mole of oxygen. And we're going to go from mole of oxygen to mole of NO2. We look at our coefficients. There's nothing in front of oxygen, so that's going to be a 1. And there is a big 2 in front of NO2 in our chemical equation. So when we multiply 0.155 times 2, we get 0.31 mole of NO2. So which is our limiting reagent, NO or O2? Yes, this is smaller. So our limiting reagent is NO. So limiting reagent equals NO. Now, the question asks, determine which gases remain after the reaction goes to completion and calculate their partial pressures. if the gas was completely consumed, which the limiting reagent, nitric oxide, would be, then that partial pressure is going to be 0. Now, from your reading, there is an equation that you have to memorize. Dalton's law of partial pressure. Because ideal gases are considered independent and they don't interact and bump into each other kinetically, this total pressure can be the sum of all your individual partial pressures. So the total pressure is going to be the sum of your NO plus the pressure of your oxygen plus the pressure of your product NO2. So basically that's what this question is asking you to do, is to solve for each one of these pressures. And for our limiting reagent, NO, the partial pressure is 0. So this is 0. And we need to find out the partial pressures of the other two. So we need to use our limiting reagent for our moles. So now we need to figure out what's the pressure of NO2. And we do PV equals nRT, and we're going to solve for pressure. So to isolate this variable, we do P equals nRT divided by V, and the N is going to be this right here from our limiting reagent, 0.211 mole of NO2. R is 0.08206 liters atmosphere mole Kelvin. And our temperature is 295 Kelvin. Our volume, now this is the key here, okay guys? This is where a lot of people mess up. This will be total volume now, remember? The stopcock is open. So our volumes now are 6.00 liters plus 1.50 liters. So it's total volume here, because this is after the reaction has been going. So when you put that in your calculator, and you see that the moles cancel out, kelvins cancel out, liters cancel out, you're left with atmosphere, which is the correct unit for pressure. You should get 0.681 atmosphere. And this is for NO2. So now we have NO2. So we'll just rewrite that. PT equals PNO plus P oxygen plus PNO2. This one is 0. This one is 0.681 atmospheres. Now we've got to do the excess reagent. So that's our product and our excess reagent. In order to do our excess reagent, we're still going to use the moles based on our limiting reagent of product. So we've got to do 0.211 mole of NO2, because that's the product. That's how many moles of product is formed from our limiting reagent. And then we're going to convert mole of NO2 using our equation, our balanced equation, to mole of oxygen. And when you look at those coefficients, you see that NO2 has a 2 coefficient and oxygen has a 1. So this gives us 0.1055 mole of oxygen. And that's how much oxygen is consumed in the reaction that would be left over. And we're going to figure out the pressure at the end of the reaction. So now we're going to do PV equals nRT, because we want the pressure, and we're going to solve it in terms of moles of oxygen. So when you isolate your P, you end up getting P equals nRT over V. And we're going to put in this number, 0.1055 mole of oxygen times our R, 0.08206 liters atmosphere mole Kelvin times our temperature, 295 K, divided by our volume. Once again, don't forget this is total volume because the stopcock is open, and this is the reaction. And this would be 6.0 liters plus 1.50 liters, which end up being what? 7.50 liters. We check to make sure our units cancel out, Kelvin and Kelvin, liter and liter, mole and mole. We're left with atmosphere. And we solve this. In our calculator, we get pressure for our oxygen is 0.3405 atmosphere. And this is after the reaction occurs. So this is after the reaction. And so when we put this up here, our oxygen is 0.3405 atmosphere. And the question was, I always like to read the question after I solve it to make sure I answered it correctly. Determine which gases remain. Did we do that? Oxygen and the gases remain oxygen and nitric dioxide after the reaction goes to completion, and calculate their partial pressures. And we did calculate their partial pressures. Oxygen's, is 0.3405 atmosphere, and nitrogen dioxide is 0.681 atmosphere. And keep in mind, when you're doing that pressure calculation, at the end you got to use total volume because your volume does change. And that is the end of that question. That question is required for your recitation problems. This is problem 5-7. A gas mixture is made up of combining 9.0 grams of argon of each. So realize that you've got 9.0 grams of argon, you have 9.0 grams of neon, and 9.0 grams of an unknown diatomic gas. So we'll just put that as X2. At STP, whenever I see STP, I go ahead and define it. So that the temperature is 273 Kelvin because it's 0 degrees, and the pressure is 1.00 atmosphere. And it tells you that it occupies a volume. So it gives you the volume of 21.34 liters. What is the molar mass of the unknown compound, the unknown gas? So what you need to do is you need to first thing you want to do is you want to take the 9.0 grams of each of these elements, and you want to solve for moles. So we're going to go from grams to moles, and then we're going to put this in the PV equals nRT equation, and for N it's going to be total moles, so it'll be moles of argon plus moles of neon plus moles of our unknown. And we'll actually have to solve for this in this equation. You'll see that, and then we'll work from there. I don't think you're going to have anything like this on the exam, but I will be sure to address it in the exam 2 review if you are. But it's still a good exercise, a good thinking exercise, and to do. So let's go from 9.0 grams of argon, and we're going to turn this into moles, so we need molar mass. I'm going to look at the periodic table and see that 39.948 grams of argon and 1 mole of argon And when you put that in your calculator, you should get 0.225 mole of argon. We do the same thing with neon, 9.0 gram of neon over 1. And then we look at the periodic table for molar mass of neon, and we see 20.1797 grams of neon in 1 mole of neon. We put that in our calculator, we get 0.45 mole of neon. Now, we're going to do PV equals nRT, and so this is P total equals N argon plus N neon plus N of X2 times R, 0.08206 liters atmosphere mole Kelvin, times our temperature. It's at STP, which is 273 Kelvin, and then we divide this by volume because we solve this in terms of P. Our volume is 21.34 liters. Do you see where that was given to you right here in your problem? So now, what's our P total? Well, P total is 1.00 atmosphere, because that's what it is at STP. Now, let's plug in our numbers as well. So moles of argon is 0.225. Neon is 0.45. And when you solve this, it ends up looking a little something like this. You get, well, see, you get 1.00 atmospheres equals, go ahead and add these together, 0.675 mole plus X, we'll just turn that into X, because it's our unknown, times, you multiply these two terms together, you get 22.40. Keep your units, see the Kelvin will cancel out, so you get liters times atmospheres divided by mole. And then does that include the, did I already take in the volume? Wait a minute. So 0.08206 times 273, and then we divide that by 21.34 liters. Now we want to isolate our variable. So let's multiply both sides by 21.34. And you do that with 1, you're going to get 21.34 liters atmospheres. And then that gives you 0.675 mole plus X times 22.40 liters atmosphere mole. And then I divided both sides by 22.40 liters atmosphere mole. So let's do that. And I cancel out my terms here. So liters atmosphere cancels out and we're left with moles. This gives us, let me put this in the calculator, 21.34 divided by 22.40 gives us 0.9526. You might get something a little different. Equals, this is moles, equals 0.675 mole plus X. So let's subtract both sides, and I got, my paper here is 0.276 mole equals X. Now, when you get that number, you're given, remember you had 9.0 grams of this diatomic compound, and now you know that this is how many moles of that diatomic compound. So what I did was I just set it up like this: 0.276 mole of this diatomic compound equals, and how would you get that number? You would do 9.0 grams of this element over 1, and then you would multiply it by its molar mass, so that would be how many grams of x squared for 1 mole of x squared, and that should give you that answer. So if you solve this in an algebraic way, it would be 0.276 mole equals 9.0 grams and that would be divided by x. So if you multiply both sides by x, then you would divide both sides by 276 moles. 276 moles, and that would give you gram per mole, right? So when you take 9 divided by 2, 0.276 moles, x diatomic, so there's the 2, equals 32.6 grams per mole. And if you divide this by 2, because it's diatomic, you get approximately 16 grams per mole. This, if you look at the periodic table, would be oxygen, or oxygen. So the identity of the unknown gas is oxygen. This is our last problem in this group. It is problem number 5-8. See if you're required to have 5-8. No, but anyway. Oh, this is kind of an important concept. A lot of your exam, you end up having problems where you do calculations, and you also have problems where we give you concepts. You need to do. That's why you need to do your reading and understanding. So this will probably be a good concept, even though this problem has you work it out and is a calculation. I have never known anybody to have to actually memorize the van der Waals equation, but I do know you have to understand its application and why. So let's just take some time to look at this. So the van der Waals equation, this is, and you also have a table. You don't have to know these. It's 5.5 table. It's page 232. This equation is, I will put right here, P plus A, so if you look in your book, you'll see it, N divided by V squared times, this is a times, now the volume, V equals NB equals nRT. So it's like PV equals nRT, but the pressure term and the volume term has been adjusted. And it's been adjusted by these parameters here. And what you'll find is in this table, you can find your A and your B, these given constants for your terms. So let's read the question. Use the van der Waals equation of state to calculate the pressure of 3.20 mole of methane, CH4, at 467 Kelvin in a 3.70 liter vessel. Van der Waals constants for methane are, and they give you those constants. Now, I want you to understand, this is the important thing. When we use PV equals nRT, we are, and you've seen it throughout, I don't know if you paid attention, this is called the ideal gas law. Okay, it's a law. That means ideal gases will not interact with one another. They will act in an ideal fashion. This is theoretical. This is not always the real case. So when you're dealing with van der Waals calculations, you're dealing with something called real gases. And real gases, this is important, if you have higher temperatures, or you have, that's important, higher pressure. If you have higher pressures, really high pressures, or you have lower temperatures, you get real gases. Now, why would that be the case at lower temperatures and higher pressures? Well, think about lower temperatures, what's happening to the volume? Okay, the volume is decreasing. So if you decrease the temperature, you're going to decrease the volume. That means the gas molecules can interact with each other. They're getting closer together. Higher pressures, you put a lot of pressure, what happens to the volume? So, not the volume, but so the volume decreases. So anytime the gases can actually interact with each other and they get closer to each other, you move away from this PV equals nRT. And the van der Waals calculations have these terms where they can adjust the pressures and volumes based on the conditions. So if you look at the temperature here, okay, so this is a high temperature. I don't know. It's kind of... Anyway. So you're correcting for the pressure and your volume. So basically, this is just a plug and chuck question. Now that you understand and you have the equation, which you do not have to memorize that equation. So we're just going to put the given into the equation. So we're going to solve for pressure. So we don't know what pressure is. And we're going to put in our A term. A is 2.273 atmosphere liter divided by mole. And this is squared and squared. And this is going to be, because that's what's right here, right? That is your A term right there. And then we find 3.20 mole, because that's N. So your N. There's our 3.20 mole divided by our volume, 3.70 liter. And we're going to square this term. We got that also in our equation. And then we're going to take that whole term, and we're going to take that times, we'll put it down here, the volume term. What's our volume? Our volume is 3.70 liters in our equation, minus, and we got our B now. B was given to us here, 0. Oh, wait a minute. Let's do N first. How many moles do we have? 3.20 mole times 0.0431. And that is liter per mole. The moles cancel out. And this is a liter minus a liter. And that is all going to equal our nRT term, which is 3.20 mole, that's N, times R, 0.08206 liters atmosphere mole Kelvin, times our temperature, which is 467 Kelvin. When you simplify these terms, you should get 0.74799 equals 1.22 oh, wait a minute. you should get pressure plus 1.700 atmospheres times 3.5624 liters equals 122.63 liters atmospheres. Then you solve for P, and you get P plus 1.700 atmospheres equals 34.42 atmospheres. P equals 34.42 atmospheres minus 1.700 atmospheres. Pressure equals 32.72 atmosphere. Now, what is the pressure using the ideal gas law under the same conditions? So we just calculated the pressure using the van der Waals equation. So this is, now what is it under ideal equation or ideal gas conditions? And that is just your PV equals nRT. So you're going to solve for pressure nRT divided by V. So what does this equal? You put in 3.20 mole from your equation times your gas constant, 0.08206 liters atmosphere mole Kelvin, times your temperature, 467 Kelvin, divided by your volume, 3.70 liters. When you put this in your calculator and your units cancel out, your answer ends up being pressure equals 33.14 atmospheres, and that's ideal. So compare the two. This is the van der Waals, we call that real gases, and this is your ideal. And so that means the pressure is higher at your ideal than it is for real. And I guess you could think about that. We've increased the temperature is pretty high, 467. PV equals nRT. So how is pressure and temperature related? This was a constant. You if you increase your temperature, I'm not sure. Okay. Anyway, sorry. Let's just leave it at that. And like I said, for this, you don't have to memorize the van der Waals equation. But I do think you should read that section and understand when ideal gases will behave, and it's considered when there's no interactions of gas molecules. Kind of try to understand that with the kinetic theory of gases. And molecules, when they're closer together, they're going to interact. This is in that section. It talks about at higher pressures and lower temperatures. And so that should be good.